All right, so this is for Calc 3. It's dealing with the worksheet 14.5, and I'm going to break this up into two parts. So this is part 1. So this is dealing with, first off, on part 1, finding the gradient or we will refer to it as del f. And of course, we have to have a notation for this, which will be replied as an upside down triangle, like so. So this is the first thing we're doing. Now, first off, you should be used to the triangle the other way. Like for example, like slope might be represented by dy dx, change of y, or like which is like dy dx. So the triangle this way says it deals with the derivative. So if we flip the triangle over, does it still refer to the derivative in some way? And the question of that is yes. All it is it still deals with derivatives, but deals with all the partial derivatives in one statement as a kind of like a vector. So yes, it's still a derivative, but it refers to the partial derivatives instead of the other types of derivatives that you've been working with. Okay, so I'll do an example of that in a second. Now the other thing we're going to get into on this part 1 is a thing called the directional derivative. Okay, which again, the notation for this is du. Now, if you look at how this is represented, say that's awful close to something like a unit vector, because that's how we've been writing our unit vectors. And the question of that is yes, it is the same thing, but this deals with a directional, a unit vector, but in terms of a certain direction that we want to take the derivative with our partial fractions or our partial derivatives. Okay, so there's really nothing new here on this first part 1 here. So it's just basically putting some stuff together here. All right, so let's do some examples here. So let's say we have a function f of x comma y comma z, and our function is x e y z squared. So if I do our partial derivatives, so partial of f according to partial of x, so do the derivative in terms of x, there's only one x there, so here's the derivative of that, so basically it'd be 1 e to y z squared. Okay, so now let's do some color. So partial derivative of, let's say, dy, so there's only one y there, but there's a chain piece, so there's x e y z squared. Now the derivative of that, of this piece, would be 2z. Okay, because the derivative of y is a 1, and that would leave you, z squared, I did the derivative there. No, we just do the derivative of y, which is 1 times z squared. Okay, now let's do green here. So now do it in terms of z. So now partial derivative of f dz, and we have x e y z squared. Okay, now we have our y, and now we have our 2z, like so. Okay, so come back and clean that one up. We have 2xy z e y z squared. Okay, and let's come back to this one here. This would be x z squared e y z squared. Okay, so what is the del f, or the gradient? Well, these are the derivatives, so but instead of putting our derivatives this way, because that represents derivatives, direct derivatives, this is partial derivatives, we would just say the gradient of f of x, y, z, and basically put all these together, just clean up the notation and put it as a vector. So you have e, y, z squared, x for e, y, z squared, comma 2 xy z e y z squared, like so. And basically this just says that you've done partial derivatives, okay, with each individual value, okay. And also notice that this is a vector as written. So therefore, if I put some notation, let's say some numbers in this, let's just do another one here. Another example. So let's say my function f of x, y, z, and let's say x, y, z. Okay. So if I want to do the derivative of these, but I want it as a partial derivative of x, y, z. So therefore it's become a vector. So the derivative of x would be 1 yz, comma, and by the way that shouldn't be comma there. Now the derivative of y be 1 xz, and now the derivative of z would be 1 and then xy. Okay, and then if I want to do, let's say f of, let's say 1, 2, 3. Okay, therefore just plug your numbers in, and basically I think you should get 6, 3, 2, like so. So basically pretty simple there. All right, now the next thing is dealing with the directional derivative. So what I want to do here, so you wrap your head around this, is come back to two-dimensional space and the unit circle. So let's say a vector, a unit vector of 45 degrees, we would have root 2 over 2, root 2 over 2. Now, if I multiply that by, let's say, 2, I have now a new vector of root 2 and root 2. And let's call this vector A. So let's go ahead and find vector A, the magnitude of that. Well, the magnitude of that would be 2 plus 2, root 4, therefore 2. Okay. All right. So let's say I'm going to think of this as partial derivatives now. Okay. So my del f would be represented by root 2, root 2. Okay. Now, my directional derivative du is basically the unit vector. Okay. Well, what's my unit vector here? My unit vector is root 2 over 2 and root 2 over 2. So this is the direction that I want to take it of the gradients of f. So basically, if I do this, if I take the gradients and multiply it by the directional derivative as a dot product, okay, so I would have, let's say, root 2 and root 2. Okay, there's that piece. And then multiply by my unit vector, or my direction that I want to take my partial derivatives, which is, again, basically a unit vector, root 2 over 2, and root 2 over 2. And if I do the dot product on this, I would get, what do I get? 2 over 2 plus 2 over 2, and 1 plus 1, which is 2. Well, notice that's the magnitude of that vector in that direction. So that's what's happening in two-dimensional, but obviously we are going to be going in three-dimensional, but it's the same thing. Okay? All right, so now let's look at it in terms of three-dimensional. Okay? So here's my sheet. And I have, here's my x-axis, y, and z. And at some point here that I'm going to find the slope of that with my partial derivatives going some here. So you have in terms of each axis and so on and so on. Okay? So I can find this by my gradients of s. So those are all my partial derivatives, like that slice of cake. Okay? Now, if I come directly down here, okay, kind of like a shadow here, and I want to take these derivatives, but I want to take it instead of like a slice it like a cake, I want to choose a certain direction that I want to go. Someplace different. Okay, so basically I'm going to choose a unit vector, but we're going to refer to this as a directional unit vector because we are in three-dimensional. And basically what we're going to do is then take these two pieces, del f times du, and we will get a magnitude of that length of that vector in that direction from that. So that's all we're doing. So let's look at an example here. Okay. So if I have, let's say, f of x comma y, and I have x squared y cubed minus y to the fourth, and we're going to find this at, let's say, 2, 1. Okay, so let's go ahead and find the del f. So del f of x, y, so basically doing the derivative by partial derivatives. Okay, so, and remember it becomes a vector then. Okay. I don't know why I put a comma there again. That's x squared times, there, sorry about that, put a comma there. So x squared y cubed minus y to the fourth. So let's do the derivative of x's first. So that would be 2xy cubed, okay, comma. Now, let's see, purple here. Now we want to do the derivative of the y's. So I have x squared, so this would be 3y squared minus 4y to the third. Okay, and now let's go ahead and plug in our values. So we're going to do this at 2, 1. And if we do that, we get 2, negative 1 would be our values. Okay. So now we wanted the direction that we want to do, which basically we're going to find the magnitude of this vector with whatever direction we want to go to. Okay. So my direction I want to go to would be a vector of, let's say, 1, 1. That's my direction I'm going to hit. Well, I need that as a unit vector. Okay, so you might think of what is the unit vector v. Well, that would be the magnitude of that, which would be 1 squared plus 1 squared would be root 2. So the unit vector of this would be 1 over root 2 of 1, 1. Okay. But that's what we refer to as our directional piece. Okay. So now if we take a del f of 2, 1 and multiply it by my directional derivative, we're going to go 2, negative 1, dot it with 1 over root 2 of 1, 1. Okay, so I'm going to pull out my scalar, and what we have here is 2 plus negative 1, which basically is 1 over root 2. So remember, we got a magnitude of where we're going. So we said we had that sheet. Okay. So here was the point, 2, 1, and we had the derivatives. So then we decided, okay, which direction we want to go. So we took this direction here, and this is the magnitude of that vector from that direction. Okay. All right. So let's do one more example, and then we'll take a pause. All right. All right. So on my notes I'll post, I think I'll have a couple examples. I got one more with a function of x sine y z. I'll let you take a look at that one online. But I want to do my second example I have on that I'll be posting, and it's this: f of x y equals x squared y cubed. And we're going to do this at the point 2, 1. But I'm going to change this up a little bit just to see if you wrap your head around this. I want to do it at an angle that I want to go here of pi over 4. So this is my direction that I want to take it. Okay, so first thing, let's find our del f. All right, so this, remember, comes a vector. So the derivative of ax squared would be 2x y cubed. And the derivative of y, x squared, would be 3y squared. All right, so now let's come back in, and we're going to do this at 2, 1. And I do believe this is 412. Okay. Now, what's the unit vector of this? Well, if you think of it on the unit circle at pi over 4, what's the unit vector of this? Well, that would be root 2 over 2 and root 2 over 2. So therefore, the directional unit vector is exactly that. So root 2 over 2 and root 2 over 2. And therefore, if I multiply that, oops, let me come back here. So directional del f of 2, 1. I have 412 and dot it with root 2 over 2 and root 2 over 2. And let's see what we got. So 4 times that would be 2 root 2. 12 times that would be plus 6 root 2. And therefore, our magnitude of that direction will be 8 root 2. All right, so hopefully that makes sense, putting just pieces together. We'll come back with part 2, which deals with some other things with this. Actually, it's a little bit different, totally, but deals with the dot product. So anyway, stop there, try to wrap your head around it, do some of the problems on this